we have good value for money for you this week with two presenters. Very complimentary presentations with Mei Chan from the libraries, who has put in place a program for teaching folks at the beginning of their data science journey, and Ramses Van Zon, who has put in place a teaching program for folks with a little more experience and sort of ramping up the size of the computers. And so we're going to start with Ramses, and he has a PhD in theoretical physics, and right now he works at SciNet. And for those of you who don't know, SciNet is Canada's largest supercomputer center. So thank you very much, Ramses. Have I frozen, or has Ramses frozen for other folks?
You have not.
I've not.
Ramses has.
Maybe we'll just give him another few minutes, few seconds. Has anybody used SciNet?
I have.
Oh, lots of people. No, Ramses is back. Hey, Ramses, are you back?
I am back.
Oh,
I got, well, I think I kicked myself out. I clicked the wrong thing.
All right, you should be a co-host. Is it working now?
Let's see. Yeah, okay. Can you see my slide?
Yeah, perfect. Yeah.
Okay, perfect. Okay. Yeah, so my name is Ramses Van Zon, and yeah, probably my favorite supercomputers are now the ones that we maintain ourselves, but that's just because they're kind of our baby, right? But I have dear memories of, and this is back in the 80s, my dad worked at the, what do you call it in English? He was a prosecutor in the Netherlands. And so he sometimes had to take his work with him home, and they gave him this portable computer, which is nothing like we expect these days. It was very bulky. It had this amber screen that was tiny, but still, when he wasn't using it, we got to sort of draw with ASCII art on it, and that was like one of my first experiences with computers. It had nothing super about it, but it was super interesting. So I've had a bit of a slow diversion of what my original path was in sciences. I started doing theoretical physics, as Rowan said, and very mathematical, and somehow got into the simulation side of things. I was doing molecular dynamic simulations because I was doing non-equilibrium statistical mechanics, and we needed simulations. And after a while, I was the one doing the simulations. Initially, I thought somebody else would do it for them. I would do the theory and then go, well, you know, I can't wait for the people in Austria to finish their calculation. Let me do some myself. And that's how sort of got the ball rolling. And then I got a postdoc at the chemistry department here in Toronto in the early 2000s. And so I got more into chemistry. And then I went to New York to do a postdoc, and that was more biological, still sort of molecular dynamic simulations. But so more and more I became a computational expert rather than a theoretical physicist. And when I realized that, I applied to work for SciNet, because I am already an analyst. I am already doing this work just in a group. And so that made it official. So what my trajectory is not uncommon to a lot of our analysts here at SciNet. And a lot of them have a PhD, have a background in research. And I think that helps us tremendously to understand what our users are going through, what they really need, and what their end goal is, rather than just being techies, which there was nothing wrong with that either, but we have a bit of perspective. So what our aim is at SciNet is to enable research computing, but I wanted to just sort of explain what I mean by that. Because it sounds very restrictive, and it really isn't. It is very encompassing. I would call research computing anything where computers are an essential element to research. So not just used to make a little plot and do and your write your papers on, but do the data mining, do data processing, machine learning, simulations, which used to be the main usage of HPC, high performance computing systems. But all of these, as far as I'm concerned, are research computing. That's what we're doing. And because it's research, it's almost never done in in a way that was done before, because why would you do research again, right? So things are constantly changing in this environment in research computing, which is interesting, but it also means that people that do research computing, just by the nature of it, will be doing some coding, will be doing some changes in things that exist. In other words, they're not going to use Microsoft Research Computing TM and click on a few buttons and get their research done. That is just not quite how it works. I almost don't have to define research computing anymore, I find, because almost all research areas now are doing research computing. It is it's the usage of this and the demands have risen tremendously up to about, I don't know, about I'd say 15 years ago or so. Research computing at the scales that SciNet is enabling was basically engineering, physics, some chemistry, and biochemical simulations were just sort of starting up, being a big thing. That's no longer true. Like there's no area that doesn't do research computing. And because there's so much demand for it, what has kind of stopped happening is everybody getting their own little digital research infrastructure, right? So you can try and apply for your own cluster, and maybe if you're a good reason, you might get it. But in many cases, they will say, NSERC will say, you know, why don't you go to SciNet? Why don't you go to Compute Canada? There are existing infrastructures. And the idea behind that is not so strange. First of all, you need, for some projects, really large infrastructure. And so in that case, the only way you could possibly do that is to collect all of the resources in one. But it also helps efficiency if you have one cluster that sometimes one group is using and another time another group. So it's never empty, never idle. It's never not doing anything. But because of that, and because the granting agencies are very much aware of this, we've seen a growth of the scale of where you get your resources. So in the past, it was possible to get yourself your own little cluster and put it in your research group, and your student would use it, and you would probably administer it and have a lot of fun with that, which is great. But that for many groups is no longer reality. Then those things were grouped together, and maybe departments now got a department cluster. Again, that could still happen, I guess, but it's not as common. Universities have tried this. One of the reasons that, and bigger universities were more able to do that than other ones. Smaller universities would have probably skipped the university step and went straight to forming consortia where they could use each other's resources. And SciNet officially is also a consortia, but it really is a consortia of U of T and the hospitals associated with U of T already. Now, even if you're a consortia of different universities and you have a cluster that you maintain, by sort of, it's demanded that that same cluster is actually accessible as a national system. So there are very few, but there are very few systems that are just for, say, the University of Toronto, or just for Ontario, or just for the University of British Columbia. There could be some at small scales, depending on a specific grant you got, but most of them are big national systems, which means even the systems that we have at SciNet can actually be used by any researcher anywhere in Canada. So it doesn't really matter. And that means we have shared resources with lots of users, and that changes a bit how we need to set this up. That's kind of why It's one of the reasons we started doing training. So large shared digital research infrastructure, so large clusters, to do all of these things, to do the data mining, to do the data science, to do simulations, to do regular or more traditional HPC stuff, lead to an economy of scale. You get way more nodes if you buy them in bulk. You get more utilization if you don't have to, if it's never idle. And since there's so many groups using the SciNet machines, they are always 98% busy. It also makes it possible to do some things that might otherwise never be possible. We've seen simulations on using up to 60,000 cores at the same time to, I think in this case, it was simulating the center of a star. And you know, that's a very tough project that needs a lot of cores at the same time. You can't do that all the time, but you can do that because you have the machine for that every now and then. Another nice thing for researchers, though, is that if you have these shared resources, you don't have to worry about the sysadmin stuff of it or the security. That there's people that take care of that, and you just do what they say, and then it's a secure and well administered system, and that's that does help. Before, and this is an area where a lot of us have grown up in. Yes, you had your cluster in your own group. You were probably doing the sysadmin stuff for it. A lot of the people that now work at SciNet might have had that background where they know how the sysadmin is supposed to happen, and that's how they sort of learned on the job. But you don't have to do that anymore. The downside, though, of having this shared system is that it's not your laptop. It's not your workstation. There, you have to adapt your workflow to fit within a shared resource. So you have to relearn a little bit how to interact with the system. You might have to learn a little bit about the tools. And that seems, at first, especially if you've already done quite a bit of research computing on your own laptop, for instance, that's a bit of a hurdle because it's not your workstation. So certain things that you are used to using, they either don't work as well or you're better off doing them differently. That's fine. It's another tool, right? It's a new tool that will enable you to do things that you couldn't do before, and you have to learn the tool. So it's not that bad, except somebody better teach you how to use this, because it is still a niche tool within the grand scheme of things. So if you Google how to install a certain package and you find some instructions, they will probably not even work on a cluster because it's written for a PC or for a Mac or something like that, and that's not what you have. So there's some relearning to do. There's some guidance that you will need, but that's okay. That's also why SciNet is here. Okay, so SciNet is officially, we are the SciNet HPC Consortium. The consortium, as I said, exists of University of Toronto and the associated hospitals. We host supercomputers. That is our foremost task. But the people here, so myself, I'm an analyst. We have about 6 other analysts, a similar amount of sysadmins. Most of them have expertise in academic research. We know about high performance computing, data science, research, data management. We have been through these things. And so we train people as well. Not just how to use the computers, but also on general subjects of things that a lot of our users need to know. We are part, because everything is national, as I said, part of the Compute Canada Federation. And there's about 5 other consortia that are also part, and they might host a system that for some cases might be more suitable for you or for your research. And so they're all coordinated by this federation, which soon will be supplanted by yet another organization, the Digital Research Alliance. So those of you that have been working with SciNet or with Compute Canada, the next year is going to be mildly confusing. Hopefully the communication will be clear, but the Compute Canada Federation stops to exist. Everything that it did is taken over by the Digital Research Alliance, which has a slightly broader mandate. It will have things like digital research or data research management as well, some software development in there as well. So it could be great. We don't know yet. but it will change. How things are working though for all these clusters actually will not change at all. There's going to be a smooth transition between the two. So I'm going to focus on what we have just because I am from SciNet, but we are working in a larger context here. So the most tangible thing of what we have is our largest supercomputer. It's called Niagara. It's not at Niagara Falls, but it is it's not even in Toronto, it's just north of Toronto where our data center is. But in any case, it's called Niagara, and it looks like this, a bunch of black boxes, and the only interesting part about it are the red Lenovo tags, because Lenovo is the one that delivered this system. And not as flashy at all. My kids are thoroughly unimpressed and say that's not a supercomputer. There's nothing super about it. Where are the lights? It's just like racks of normal computers. Okay, but that is the reality of supercomputers, which is actually very honest. We really just have 2,000 very beefy computers linked together, if you want to think about it. So each of these computers, we call them nodes, has 40 cores, and they're connected by a network. The network is very fast and well connected, which makes it possible to use all of these nodes at the same time for the same problem. So that makes it super. But this is the architecture. Each node is on purpose. These are all the same nodes. Some supercomputers that you will find will have some nodes that have this specs, the other specs for other nodes. Some will have a GPU, others will not, which makes it a little tricky to find out. This is by design a homogeneous system. You ask for how many of these nodes you want, and you always know what you get. So it's kind of simple. The nodes have a fair amount of RAM, about 188 gigabytes. On this system, connected to this system, is a bunch of disk storage. Latest count I had 17 petabytes there. Obviously, you are not all going to get that 17 petabytes, but that's the size of it. There's tape storage for backup and archival, which is about twice the size, and is still growing. Tape is easier to expand because it's buy new tape than a hard drive. So that's the system, and obviously you could use it for anything you want in principle, because these are fairly run-of-the-mill cores. There's many of them, but they're just x86 cores, the same that you would probably have in your workstation or your laptop. What makes this different is that this is a shared system, and it's a remote system, so you have to connect to it somehow. And so people connect to this primarily using a tool called SSH, stands for Secure Shell. So it's a secure way to connect, and it all works on terminals. There is a way to interact with it in a modest amount using a Jupyter Hub. And for transferring data, you can use a web interface called Globus. But by and large, people work on the terminal. And that is by itself different for most people that start out using a supercomputer. But that is how it gets used. And we have a few smaller systems as well. We have a GPU cluster called MIST, which has a different architecture. But if you want to play with GPUs computing, then that's your system to start with if you already have a SciNet account. There are GPUs on the other Compute Canada clusters as well, so that is another possibility. We have an AMD GPU cluster, which is just for U of T. And we have a Teach cluster, which is actually just a portion of an old supercomputer we had lying around. We strongly advocated to keeping a small piece around for teaching. So that is, if you're teaching a course at U of T, again, this is U of T specific, we can give you access to that, and students can play around on that without having to use any of the official resources of Niagara. So Niagara is a national system, but for training, sometimes you don't want your students to be on there. You want to isolate that or do something special. That's the Teach cluster. So that's what we have. Let's see. But as I said, there are differences in how you work on such a system versus your own. And there is no nice web interface where you point and click and you run your stuff. It all goes through a command line. There are ways to schedule your jobs because there's more users and more jobs in the queue than can run at any given time. So you don't log in and start your stuff. You have to submit it. So there's a bunch of things to learn on how to use this, and we're here to teach you how to do that. We have a website dedicated just to all our teaching. It's education.scinet.utoronto.ca. And the first thing you would do once you've got an account on the SciNet systems is to take the intro to SciNet and Niagara. It will explain how you log in. It will explain how things are set up, how you get software on there, how you get your data on there, how you work with it. That's your start. Now, because people will have to work on a terminal, they'll have to know a little bit about how to work with a Linux shell. That is okay. Depending on your level of needs, you don't need to know a lot, but you need to know a little bit. And so I highly recommend to take an intro to the Linux shell, which we offer as well. There are others that you can find online, like you can learn about Linux, but it's always nice to have it in a context where you're going to use it. Other things we teach, we actually have some of our workshops grown out into grad courses. So if you're a grad student, you might, and you're interested in this kind of stuff, we have a grad course on scientific computing, on data analysis and biostatistics. These are given in collaboration with other departments. SciNet is not a teaching department, so we have to partner up with physics for the scientific computing. Medical science is doing the data analysis. Biostatistics goes from, I think, Scarborough. There's another course we have with biochemistry. So this is things we can also collaborate with others. Like if you go, hey, I'm going to teach a course, but I could use some supercomputing in it, just ask us. By the way, instead of the date on my slides, I've put our email, support@scinet.utoronto.ca. Any questions you have on using SciNet, just send it to there and the whole team gets that, and whoever is responsible will pick it up. We do courses on scientific and parallel computing, courses on data management, parallel I/O, databases, machine learning, some AI, like deep learning, neural nets, that kind of stuff. And so those are sort of our regular throughout the year courses. In the summer, and this is starting to be possible again, in the summer, we also have summer schools. We didn't have a real Ontario summer school last year or the year before because of obvious reasons, but there's going to be an Ontario summer school. So here's where we collaborate with other consortia in Ontario, SharkNet and CAC, which have also got machines and training. And so it's a multi-week event with sort of intensive training on all kinds of topics. This is still being fleshed out exactly what it is. SciNet is also involved in an international summer school. Unfortunately, there the deadline for applying has been long past, but since for the first time in years, the intention, if nothing else happens, is to have this be live in person in Greece. So that's very nice. This is a select set of students that are doing HPC, so high performance computing. We coordinated together with our American counterparts, Exceed, the Europeans, Embrace, and the Japanese counterpart, Riken. Riken is the top 1 supercomputer in the world, so these are the big boys, if you want. The formats vary a lot. What happens during the year is either a 1 hour or 1 afternoon or several days sometimes, but that's much. The grad courses, of course, are multi-week, much like a grad course usually is. So it varies. Check out the website to know exactly what's going on. Also, if you get enough courses, you can get a certificate from us. So most of these, apart from the grad courses, are not for credit in terms of like towards your graduate degree. But since we know you took them as SciNet, we have no issues like certifying, saying that you have indeed taken 36 hours of this and this topic, and so we'll give you a certificate just to prove that you've put in some work to learn these things. So the first thing to do to start using SciNet or any of the clusters is to get an account. It's a mildly more involved process than I would like it to be, but it is not difficult. The link here shows where to get the information, but the idea here is that you don't get an account just by being a person. You get an account by being involved in research computing, and you know that. And how do we know that? Well, your PI, or if you are a PI, you will request an account first at Compute Canada. So Compute Canada has a Compute Canada database site, and you get your account. And if you're a faculty member, one of our people, most likely our CTO, will check whether that indeed makes sense. Who you are is who you are, and then you'll get your account. And from that account, now you can sponsor as a PI your students, your postdocs, and collaborators. So the PIs vouch for their students, postdocs, and collaborators, so that we don't have to check everybody ourselves. And so they request a Compute Canada account. There's a special identifier that the PI has that they have to fill into their form, and then the PI gets an email that asks, is this really somebody that you work with? And if they say yes, you have your account. So that gets you the account in the database. Then you need access to Niagara. That's a one-click process on the CCDB. So follow the link on here, you click it and you say opt in, I want access to Niagara. And then a few days later, you get an email saying everything is set up. Good. That used to be all you had to do. And then you could log in with your password, the password that you set on the CCDB. There's been a large push to more secure practices. And I think that is more important, especially on these large CR systems. And so one of those extra security things is that a password is no longer viewed as a very secure way to log in. It's too easy to brute force yourself in. And so we're using a thing called SSH keys to have you log in. So that's your next step. Again, if you either go to the intro to SciNet, we will explain this in detail, or if you go to the get an account and then follow the links, you can get our wiki page. So annoying, but only needed really once. And once you're set up, you get access to Niagara, you get access to MIST, you get access to our education site, you get access to the other clusters in Compute Canada. There's 4 general purpose clusters with different specs. So for instance, you might need, you have a computation that needs a lot larger memory, and the compute nodes in Niagara have 188 gigabytes, and that is not enough for you. Then there's some nodes in the other clusters that have that, or you need a lot of GPUs, more than MIST can give. You can go to those clusters. That's okay. Okay. If you have your account, you could run. As I said, I would really strongly recommend you do your intro to SciNet first, and then an intro to Linux shell if you're not familiar with that. And then you can take your pick. The SciNet site has a list of courses you can enroll yourself. You just have to log in. But what's also nice, even if for those of you that aren't going to use this or don't get an account, all the material on there is freely available and accessible. You just can't get credit or can't do the exercises, but you can see the slides, you can see recordings if there are recordings, and most of these are now virtual, and so recording is actually a fairly simple extra thing to do. So there's a lot of resources here, even if you're not taking the course, just to learn. For instance, if you wanted to know about the Intro to SciNet now, you just missed the last Intro to SciNet this Wednesday, you can look at the recording. So those are our resources. Okay, I took a little longer than I expected for just 10 slides, so I apologize, but I am happy to answer any questions, but we might want to, I don't know if we want to do first May have talk.
Yeah, I have a lot of questions, but yeah, thank you very much, Ramses. Really appreciate your presentation and overview of SciNet. But you're right. We might ask. May, are you okay to present?
Yeah. Let me just get my slideshow going here.
And then we'll do questions all together at the end if we have time.
Sure. Just gonna share screen. There we go. All right, are you able to see my title slide?
Yeah, looks great.
Okay, great. Hi, everybody. I'm May Chen. I'm with the University of Toronto Libraries. I'm the head of metadata services. What my department does is describe the resources that the library curates and collects and acquires for research purposes. So it's a little weird, I think, for me to be talking about this because I kind of come from the back end and not typically associated with technical skill development, but I do think the work that I do and the struggles that I see that people have from within the profession kind of got me to this place. So so the title of my presentation is Room for Everyone, the Carpentries as a Driver of Conclusive Communities of Practice in Large Institutions. And this is a work presentation. A lot of the deck here is taken from a presentation that I gave with Elizabeth Park, who is a senior research associate from the collaborative digital research space at University of Toronto, Mississauga. So I'm just going to leave her name on the slides, even though she's not here today, because she was a big part of coming with this content with me. So following after Ramses' presentation is actually really, I think, a really good segue because you know, with all the talk of training and also sort of all the presentation of stuff, right? Like the machines and the programs. And so I just want to emphasize here for my presentation, it's about talking about people as infrastructure. And this is a photo that I had taken of a rugby game just before I moved to Toronto, and this was my best shot. And I've always thought this is such a wonderful shot of people working together to, you know, strive towards a particular challenge. And it takes teamwork and it takes everybody. And yeah. So what I'm talking about today is how the University of Toronto Libraries brought the carpentries to the University of Toronto, and to talk about how that presented an opportunity for inclusion around computational and data literacy for everybody. And by everybody, I'm kind of ambitious here. I'll get to that in the next slide. I'll be also talking about sort of unexpected alliances and the connections that came out of that has come out of this work of bringing the carpentries to the university. I'll touch on some ongoing impacts of the project and talk about the I guess challenges of sustaining a community of practice. So actually, one thing I could put in the chat here is I don't have a whole lot of time to give background, but for a more detailed story on how it actually came to how we actually brought the carpentries to the university back in 2019. I'm posting something in the chat because we had given a presentation at another conference a little while back. And so maybe some background here is that there's kind of two layers to the carpentries coming to the University of Toronto. If you're not familiar, the carpentries is an international, I guess, grassroots open education kind of community of practice. And the mission is to basically help researchers worldwide to obtain the computational technical skills they need to do research. And a lot of the, I guess, vision is targeted at the novice learner. And by novice, the novice range can be quite large, but we're talking about like the novice. All right, let's go here. So one of the reasons why we drew on the carpentries as a resource to promote technical skill learning was because they had a pretty well-developed community of practice. They have a really great vision, code of conduct. They have a vision around inclusivity. And so we thought, why not bring that back? Like, let's take a little bit of their DNA and inject that into the U of T community. and just open up the opportunity to empower as many people as possible, or whoever's interested from whatever academic unit, to be part of teaching technical skills. And so I've modified these slides to include what we've been doing this year. So in 2019, the first iteration of this project was to obtain a lower level membership that enabled us to train about 25 instructors, to teach technical skills. And then the pandemic hit and we couldn't really do much with that. But then when there was an opportunity again in 2021 to kind of jumpstart that. And so with 2021, we were able to obtain a higher level membership that allowed us to train 50 people from the community. And yeah, it's kind of been a really fun and interesting process, meeting a lot of really different people along the way. So in terms of finding people for the training seats. So these are training seats to teach people how to teach technical skills. Then we had a fairly, I guess, careful rubric about how to select people for instructor training. We wanted to have a nice balance between folks coming from STEM and social sciences and humanities. We wanted to have a really good mixture of different kinds of students. So graduate students, undergraduate students. We tried to reach faculty in the first time in 2019, and there were no takers. But in the second part of the project, we had a few faculty come and take the training, which was fantastic. And then, of course, people from the library and the research environments too. So we really, and we wanted to cover like people from all the campuses as well, because you know, it's noted that like the St. George campus tends to be just very, very dominant. The other considerations around training people were to select people sort of based on sustainability. So trying to assess what their staying power was or commitment to this type of, I guess, community of practice, of being inclusive of novice learners, and then just discerning if they have a shared vision. And they would express that in their application, indicating that maybe they have volunteered in a community like Ladies Learning Code or the U of T Coders Club. And yeah, so it has made for a very pool of people that have come through the program. And in 2020, so this is just before the pandemic hit, we had hoped to organize a whole series of workshops, but we only got to organize 3 out of 6. But we did get to organize 3 workshops that is around the curricular track that the Carpentries offers. So what's really great about this community of practice is not only do they teach people how to teach technical skills, but they also offer like open curriculum for the community to contribute to that is vetted actually for the novice learner. So there's 3 curriculum tracks that form the Carpentries. That's data, carpentry, which is more about data literacy, software carpentry, which has to do more with programming, and library carpentry, which is sort of a blend between the two. So, and then what we didn't get to do that year was to organize carpentry's workshops across the tri-campus with the aim of targeting USRA students to prepare them for their labs. Yeah, but that was too bad. So we had made those workshops open to anyone. I think that's kind of not a condition, but that's just a good practice to allow anybody from the community to register with maybe like a target on a particular group. And then the idea would be that an academic unit would sponsor and organize and host these workshops. So it's sort of like a decentralized model. It's not like any one unit or like one person or team like would organize everything. Like my personal philosophy here is that these literacies, computational and data literacies, are kind of like, it's like a basic literacy now. It's like the new, I don't know, it's the new reading skill, right? And that everybody should know how to do it. And if there's just too many people to reach. So just to give you an example, like of sort of, I mean, we all kind of know this, but I always find it fascinating to think about how big U of T is. You know, it's like over 100,000 people across 3 campuses. And yeah, I mean, there's going to be a lot of people who do know how to code and process data and clean data, but there's many more who don't. And I'm also picking up on the fact that maybe people coming from high school, you think people coming from high school would have that built into their K-12 curriculum, but still not. And I'm still hearing through, you know, like just anecdotally, students coming through humanities, particularly not feeling really confident in acquiring these skills. And I guess where I intersect with that most is just people that I work with, people who I work with, and they don't really feel they can get into working with data, or, you know, working in with Unix, or knowing how to work with GitHub or something. So yeah, I'm just sort of getting a sense that a lot of people don't feel like there's a place for them because they don't know how to interact with tools, or they don't know how to think in a certain way to get a machine to do something the way they need them to do, or they don't even know that the machine should be able to do something. It's something sometimes as basic as that. So I just wanted to highlight some of the connections made from the various iterations of this project. So what I have highlighted in sort of like this maroon color and bold are the new connections formed from the second version of this project. So I'll just kind of go through each really quickly, but the U of T Coders Club has been really, really great in terms of sending people for, or sponsoring people for instructor training, because they're constantly offering workshops, offering workshops. For the project team this year, we were able to bring in somebody from the Math and Data Library and New College Library to represent a liaison librarian view. And UTM, like the Mississauga Library, was part of it from the first round. And then we were able to bring in somebody from Scarborough this year, which was great. And UTM Research Office. And then we had a representative from ICCIT, and the Critical Digital Humanities Institute and Faculty Information are also collaborators. So with CDHI it is like with Elizabeth Park, and with the Faculty of Information is Rohan. So Rohan has been a really active member of our team to build bridges. And what's really been wonderful about the project this time around was that CDHI and the Faculty of Information kicked in some money to contribute to the membership to guarantee seats to develop instructors in their own networks, and they have been able to do stuff with that. And we also had an opportunity to organize something with the Robert Gillespie Academic Skills Center. The collaborative digital research space run by Elizabeth Park has been a great space to host events. We had somebody trained from the research office that moved to CIFAR, but is still active in our with teaching. And then most recently, thanks to some outreach efforts from the project team, we were introduced to Ramses about their educational offerings. We also had a chance to connect with AceNet, who has a Carpentries membership as well, because they noticed that in the maritime network that they're part of, that there's many novice learners. And then we also, thanks to Rohan's bridging work, also made a connection with the computational and data science education community of practice. So I'm very, very happy about these community connections. So in terms of ongoing impacts of the project, I don't know, maybe I can sort of share my slides later. There's a lot of detail here, but we have like 25 that I am aware of who have completed certification from 2019. And then we've got at least 30 in the process of certification. And we have also developed to train the trainers so that it could be a little bit more self-sustaining. Maybe something to highlight that was of great interest coming out of this year's outreach efforts is that the University Health Network reached out to us to organize specifically a carpentries workshop. They knew exactly what they wanted, and they wanted some trainers, which we could supply. And then also as a result of that, they were interested, had a chance to promote the map and data offerings, and they were interested in that. And I believe there has been some more personalized requests there. So maybe I had this slide here to talk about the challenges of sustaining communities of practice. So this is sort of our process, was to introduce some external DNA, and then sort of keep unlikely, what we mean by keep unlikeliness at the forefront is just like, who is unlikely to connect with each other, and who can we build bridges between, and who can we introduce that may not intersect in any other way. And we saw a lot of those unlikely connections happening through our workshops. Just kind of keeping in mind networks over silos. We've had a number of setbacks, and I've learned to take this whole project with sort of a really long-term view. I'm still working on what it means to make this all sustainable and equitable, because it's sort of something I do on the side of my regular job. And one thing I do think is outstanding is kind of doing an assessment of impact. And I've been hearing like interesting things like coming out of this. So when I measure impact right now, it's like I'm paying attention to the next ring out. So if I'm getting connections directly, that's what I'm considering impact. But I'm hearing a ripple effect as well. Like, for example, I had a nice conversation with Rohan recently and discovered that some of the instructors that we trained from the summer last year are helping out in his project. And so like, if I was able to like learn about sort of similar types of ripple effects in the community, then I would be really, really happy. But right now it's sort of, right now my focus is to just make the opportunities available and try to like encourage people to see that there's a place for them in the whole like open research ecosystem.
Thanks very much, mate. Really appreciate the overview of what you did and the incredible training that you put together. It's quite remarkable. And are there any questions for Ramses or May? I'll just get us started with the usual, and then I'll stop recording. But May, do you have any books that you recommend? And then I'll turn to Ramses. May, do you?
Yeah, I do have a book that I recommend from the instructor training that is often shared there, and I'll put that in the chat. But I just wanted to let the group know that I have to go at 1 o'clock. So yeah.
No, we'll end at the top of the hour. And Ramses, do you have any books that you recommend, folks?
The truth is no. Not because mostly because things change a lot in this, and the best way to learn, I think, is just to check out the training offerings. That's one of the reasons we keep everything open. Like you check out the slides of old events, and that's the best way. You can learn Linux any old way. You can learn Python any old way. And so I don't have a favorite book for things like that. I'm sure there's better and worse ones, but when it comes to the sort of the hands-on training and the actual practical things you need to know, there's nothing that's up to date enough to tell you that.
So thank you very much. I'll stop recording. Kelly, did you have a question?